On the morning of June 10, 2000, London unveiled a bridge that seemed almost too elegant to be real. It stretched across the Thames like a thin silver blade, low, clean, and apparently effortless. On one side stood St. Paul's Cathedral, on the other, Tate Modern, and between them was a bridge designed not to dominate the skyline, but to almost disappear into it. Then the crowd stepped onto it. At first, the movement was subtle, a slight shift beneath the feet, the kind of motion you might dismiss as imagination. Then the deck moved again, left, then right. People widened their stance. Hands reached instinctively for the railings. Some laughed, others slowed down. A few stopped altogether. And before the day was over, London's newest architectural landmark had received a nickname no designer would ever choose voluntarily: the Wobbly Bridge. But the wobble itself is not what makes this story extraordinary. Bridges move. Engineers know that. Designers plan for it. What makes this case so fascinating is that the crowd was not merely causing the bridge to move. The crowd was reacting to the movement and, without realizing it, helping the bridge move even more. For a brief moment, thousands of pedestrians and hundreds of meters of steel became part of the same machine. And that machine had created its own rhythm. To understand how that happened, we first need to clear up one important misconception. The Millennium Bridge was not collapsing. Its cables were not about to snap. Its foundations were not failing. The deck was not tearing itself apart. Structurally, the bridge remained standing, but people could not comfortably use it. Engineers call this a serviceability failure. That phrase sounds almost harmless. It was not. A bridge does not have to collapse to fail. If people feel unsafe crossing it, if they must grab the railing to stay balanced, then the structure is no longer doing its job properly. The bridge was strong enough. It simply was not behaving well enough. And I think that distinction is important because the easy version of this story is that someone made a weak bridge. That is not really what happened. The engineers had calculated the loads. They had studied ordinary vibration. They had checked whether the structure could carry the expected crowds. What opening day revealed was something more difficult to predict. The bridge was not only carrying pedestrians, it was communicating with them. The Millennium Bridge stretches 325 meters across the Thames with a main span of 144 meters. Its defining feature is its unusually shallow suspension system. Traditional suspension bridges often place large towers and high cables above the roadway. Here, the cables were pushed low and outward, preserving the view and giving the bridge its distinctive blade-like profile. It was a beautiful decision. It was also an ambitious one. The cable geometry was extraordinarily flat, with a span-to-dip ratio of roughly 63:1. That helped produce the bridge's elegant shape, but it also created a slender, flexible structure with several natural ways of moving, and flexibility by itself is not a mistake. Every bridge moves, it expands in heat. It contracts in cold, it bends under weight, it vibrates when people or vehicles pass over it. A structure that never moved at all would probably create a different set of problems. The surprise was not that the Millennium Bridge moved. The surprise was how it moved and how quickly the crowd responded. The troubling motion was lateral, side to side, left, then right, across the width of the deck. A person walking naturally produces a small sideways force with every step. Usually, that does not matter. Different people step at different times, so their forces are scattered. Some push left while others push right, and much of that movement cancels out. At least, that is what you would expect. The moment the bridge began to sway, the crowd stopped behaving like a collection of independent footsteps, not because everyone suddenly decided to march in perfect formation. That popular explanation is memorable, but it is too simple. The real mechanism was more instinctive. It was balance. Imagine standing on a floor that slowly drifts to your left. You do not solve an equation. You do not consciously plan a corrective step. Your body simply reacts. Your next foot lands a little differently. Your hips shift. Your center of mass moves back over your feet. Then the floor moves right. Your correction reverses. This happens automatically because falling over is generally something the human body tries very hard to avoid, but every correction has a consequence. When your foot pushes against the floor feels that force. Now replace the floor with a flexible bridge and replace one person with hundreds. A small movement of the deck changes the way people place their feet. Those altered steps create a lateral force. If that force arrives at the right moment, it adds energy to the bridge's movement. The deck moves slightly more. That stronger movement creates stronger balance corrections. Those corrections return a stronger force to the deck. The bridge changes the footsteps. The footsteps change the bridge. And the loop begins to feed itself. This is the point where the story stops being about a crowd standing on a structure. The crowd had become part of the structure's dynamics. That idea is easy to say, but its implications are enormous. Engineers often simplify the world in order to model it. A crowd may be represented as weight. A pedestrian may be represented as a repeating force. A bridge may be represented as a structure with mass, stiffness, and damping. Those simplifications are necessary. Without them, engineering becomes impossible. But every model has a boundary. And sometimes, the most dangerous behavior lives just outside that boundary. On the Millennium Bridge, the missing piece was the relationship between human balance and structural movement. Pedestrians were not passive loads. They could feel the bridge, they adjusted to it, and the bridge felt those adjustments in return. In engineering terms, the crowd could either help remove energy from the motion or add more energy to it. Sometimes pedestrians acted like positive damping, helping the sway fade. Under the wrong conditions, they produced the equivalent of negative damping. Instead of calming the movement, they fed it. Of course, that raises a question. If people naturally adjust their balance, why does every crowded bridge not begin to wobble? Because every moving structure is also losing energy. Materials flex, connections rub. Friction converts motion into heat. Different forces interfere with one another. With a small crowd, the bridge may remove energy faster than pedestrians add it. The motion fades. Most people never notice. But as the number of pedestrians increases, the balance can change. The added lateral force grows. Eventually, the system can cross a threshold. Beyond that point, energy enters faster than the bridge can dissipate it. The deck moves more, people correct more strongly, the crowd returns more force, and what began as a barely noticeable sway becomes something everyone can feel. Nothing needs to crack, nothing needs to snap. The system only has to cross the line between losing energy and gaining it. That is what makes feedback systems so unsettling. They can look stable right up until the moment they are not. It would be tempting to blame the bridge's unusual appearance. Perhaps it was simply too thin. Perhaps the designers had sacrificed engineering for beauty. But I think that interpretation misses the most valuable part of the story. The investigation showed that this was not merely a strange problem created by one unusual bridge. Other crowded pedestrian bridges with sufficiently low lateral frequencies could experience a similar interaction. Millennium Bridge had exposed a gap in the wider understanding of how crowds and flexible structures behave together. Opening day had become an accidental, full-scale experiment. Unfortunately, the test subjects were the people already crossing the bridge. The bridge was closed. Engineers began collecting measurements. They studied the way pedestrians responded to movement. They examined other structures. They built new models connecting deck velocity with crowd force. And then they faced a difficult design problem. Stopping people from crossing the bridge would eliminate the wobble. It would also eliminate the purpose of the bridge. Making the entire structure much heavier and stiffer might reduce the motion, but that risked destroying the elegant form everyone had worked so hard to create. The challenge was not simply to stop the bridge from moving, it was to preserve the design while changing the way the system handled energy. And this is where the repair becomes, in my opinion, even more interesting than the failure. The engineers did not try to overpower the bridge, they taught it how to calm itself. The retrofit used two main tools. The first was the fluid viscous damper. Imagine a piston moving through a sealed chamber filled with fluid. As the piston moves, the fluid is forced through a controlled path. The resistance converts organized motion into heat. The damper does not make movement impossible. It simply removes energy every time the structure moves. Cycle after cycle, the vibration weakens. Installed beneath and around the deck, these dampers could target lateral sway without changing the bridge's appearance. The second tool was the tuned mass damper. This solution sounds almost contradictory. To reduce unwanted movement, engineers added a weight specifically designed to move, but the key was not whether the weight moved. It was when. A tuned mass damper is connected through springs and damping and adjusted to respond to a particular vibration mode. As the bridge moves one way, the tuned mass responds out of phase. Its movement draws energy away from the motion people feel. It is less like holding the bridge still and more like disrupting its rhythm. And that, to me, is the elegant part. The original bridge had entered an unwanted dance with the crowd. The retrofit introduced carefully designed partners whose only purpose was to break the rhythm. Fluid viscous dampers resisted lateral sway. Tuned masses controlled selected horizontal and vertical vibrations. Together, they changed the energy balance of the entire pedestrian bridge system. Crowd could still apply lateral forces. The bridge could still flex, but now the structure removed energy faster than the feedback loop could build it. Prototype systems were installed and tested on the real bridge. The results matched the predictions. After months of investigation, modeling, installation, and testing, the Millennium Bridge reopened in February 2002. People crossed it again. The bridge still moved because all bridges move, but the runaway lateral response was gone. The engineers had not made the structure perfectly rigid. They had done something more intelligent. They had made its movement controllable. And that is why I think the Millennium Bridge deserves to be remembered as more than an embarrassing opening day failure. It revealed something fundamental about engineering. People are not always passive users of a system. We sense movement, we adjust, we compensate, and those reactions can return forces to the machines and structures around us. A design may correctly model every component and still miss the behavior created by the connections between them. So what failed on the Millennium Bridge? Not a cable, not a tower, not even the idea of a slender, beautiful crossing. What failed was the boundary of the original design question. The bridge had been analyzed as a structure carrying pedestrians. Opening day revealed something else, a structure and a crowd continuously responding to one another. Steel moved the people moved the steel. And hidden between those two reactions was a behavior neither could have created alone. That, more than the wobble itself, is the lesson worth remembering. Because some of the most important failures are not hidden inside a broken component. They exist in the space between systems we thought we understood separately. And on the Millennium Bridge, that space was no wider than a human step.